Hi everyone, in this video I will talk about optical switching. This topic involves some basic knowledge about optical circuits and fibers, so it is recommended that you understand relevant terms in advance. Okay, let's start with the fiber. It is consists of three parts: core, cladding, and jacket. Core and cladding are made of glass and jacket is made of plastic. Note that cladding has a lower index of reflection than core, so light can be kept in the core by the phenomenon of total internal reflection. Compared to other mediums, optical fiber is good for insulation, immune to noise, and more importantly, it has no attenuation for wide bandwidth. That is why we choose it to transmit light. It should be noted that fiber has different modes and different kinds of index to transmit light. Basically, multi-mode is used for most short-distance communications, and single mode is used for most long-distance communications. Now let's move on to all optical networks. With all optical network, we can have a very high transmission speed and a low power consumption. It is also transparent and environment friendly, but it is hard to monitor errors. Apart from this, switching equipment can be quite expensive. Based on these features above, it is primarily used in core networks. Now here is the comparison between optical and electronic. As you can see, both are quite distinctive. When talking about high transmission speed of fiber, we actually ignore the fact that nowadays the speed of optical electronics are much slower, which means a lot of waste. To solve this problem, we use multi-optoelectronic systems, and wavelength division multiplexing is exactly what we need. In this way, different wavelengths are combined and transmitted through the fiber. But how to demultiplexing those signals in the receiver side? Well, there are several ways. We can demultiplex by reflection, by diffraction, by interference, and by filters. Now let's talk about microelectromechanical systems. This is one of the technologies that make switching optically by being implemented on silicon using lithography. MEMS are all wavelength switching. The devices are all made of mirrors, and they are wavelength insensitive. It should be noted that the MEMS require precise positioning of mirrors to achieve switching. Here is what MEMS look like in two-dimensional and three-dimensional ways. Now let's talk about controllable refractive indices. Well, to control refractive indices, we can apply electric field, sound, or light. And by controlling it, we can achieve dynamic demultiplexing. It also serves as the basic for the other interferometrics, just like this. With these filters and gates, we can control the delay of phase to combine the wavelengths or to filter out the wavelengths by adjusting the phase difference. In this way, it can be seen as a very important component for combiners and filters. And with such basis, we can roughly construct the switch by using splitter, combiner, and filter. Each input is split between N outputs, which are amplified by an EDFA as filter. It should be noted that the combiner actually has only one active input. Finally, let's briefly talk about photonic packet switching. In optical packet switching, the data is divided into two parts: payload and control. Payload travels over light path from source to destination, while control information, on the other hand, incur optical electronic conversion. The details is shown in the picture. That's all about this lecture. Hopefully this video can be helpful, more or less. Thank you.